This is Pure Book 2, Exercise 6A. Okay, so we're going to be looking at 6B, excuse me. We're going to be looking at sec, cosec and cot graphs. But to start off with, I want us to be thinking about the graph of y equals x squared. And is there a way we can figure out the graph of y equals 1 over x squared? Because if we can crack a technique of moving between these two graphs, then that's going to be helpful for what is coming up next. Now, it's important to think about the numbers, the number 1, because we're going to do something to the y values of our original curve and help plot the curve that we see on the right, the reciprocal curve. So 1 over 1 isn't those points where we have a y coordinate of 1 over 1 is 1. So our y coordinates at those x values remains 1. However, if we look at the y coordinates between these two numbers, the y coordinates are less than 1. So if the y coordinates are less than 1 over that should make a bigger number. So our y coordinates between -1 and 1 are all bigger. And the smaller the original y value, the bigger the reciprocal y value. So 1 over something really small becomes something very big indeed. In fact, at 0, our y coordinate becomes infinity. You can't see it marked on the graph, it's there by the asymptote. Now if we look at the y coordinates on this part of the graph here, they're all bigger than 1. So if you do 1 over a number that's bigger than 1, it gets smaller than 1. So the y coordinates leapfrog this dotted line where y equals 1. So that's the important thing. If they're below the line, they jump above the line. And that's the critical idea that we're going to be using to create our graphs. Here we've got the correct graph just by thinking about the smaller y gets, the bigger it gets when we do 1 over it. Okay, so we're going to start with y equals sec. We're going to derive this graph by using the graph of cos of x. So here is our graph of cos of x appearing on the screen. It's nice to put a bit of detail in it, especially in our notes. Less so when we're doing exam questions under time pressure, but you can do this under time pressure if you need to. In fact, I think it's better to derive it each time. You'll remember it much more quickly. Okay, so we're putting in the lines where y equals 1 or y equals -1 as well. Now those are going to be important for the parts of the curve below the x-axis. So we're starting by looking at this chunk of curve here. It's all below the y-axis, all below y equals 1, except for this point here, which equals 1. The smaller y is, the bigger it becomes when we do 1 over. So that's where we get this curve from. Now if we do the same thing to the bit of curve between 90 and 270, where we are equal to -1, 1 over -1 remains -1, so that spot doesn't move. The further we move away from the y equals -1 line, the further away our new y value will be, and we will get further away from the x-axis, but in the negative direction. Let's do one last bit. We'll look at the part of the curve here, remembering that when we do 1 over, we are leapfrogging the line y equals -1 and getting much bigger if we're very small. And this gives us our graph. We'll take a little snap of that and get rid of all of our working. This is the graph of y equals sec x. It's periodic in the same way that cos is periodic. It goes on forever in both the left and the right direction. And we can mark in a couple of extra points. Now what you might get asked to do is sketch a transformation of this. You can see our little example down here. We are doing just basic transformations. It's a sketch with a scale factor of 1/3. So we're squidging everything up. So if you think about it, it's going to be the same sketch, but we're multiplying all of our x coordinates that we see by 1/3. And in fact, those coordinates are largely just on the x-axis. So it is the same sketch, but then with the stretch of the x-axis. So all those coordinates will change. Okay, it's another go at the almost identical idea. We're looking at Sine X this time, so let's do a sketch of Sine X. And we'll think about the peaks, and we'll think about the roots. So we'll mark on as many bits of information as we can. So we're going to do 1/, to each of the y coordinates. Remembering if the y coordinate is very small when we do 1/, to it, it becomes very big, either in the positive or the negative directions. Let's start by doing an x-axis for our new sketch of y equals cosec, and we'll put some of those key numbers on as well. So if we look at the peaks first, the peaks are not going to move because 1/1 is still 1, and 1/-1 is still -1. So the peaks and the troughs are going to stay where they are, only they're going to change into minimum points if they were maximum. That's the key. All of our new values are going to be bigger than 1 or less than -1. And you can see it's a very similar curve to y equals sec x. Just as y equals sine x and y equals cos x look very similar. Okay, so this is our graph appearing. We have asymptotes wherever we have roots on the original trig function graph. Okay, there we go, y equals cosec. Now, if we wanted to then sketch this function, we would just be subtracting 1 from each of the y coordinates, shifting the entire curve down by 1. So we'll mark on all relevant points and shift everything down by 1 unit. Okay, for final one, we're going to start with the graph of tan. We'll do this one with radians along the x-axis because the question we're going to answer, x is clearly in radians because there has been a pi used inside our function. So that's what's motivating me to use radians. And we sketch y equals tan. it's the blue line, and it is periodic with period of pi. And there we go, we've got 3 curves is enough. Now the trick here, we're going to quickly sketch on the y equals 1 and the y equals -1 line. Remembering, if we're below the line, we flip above it as we reciprocate. And we're going to start by looking at the first part of the curve here. When we're below the line, we're going to flip above it, and when we're above the line, we're going to flip below it. Okay, we'll put on all the points that do not move, those that are exactly 1 or -1. But then the lines flip above or go below the line y equals 1 or y equals -1. And when we do that, we get this really rather unusual thing, that it's in fact a reflection of our original graph. That is the same shape, it's just been reflected. Very unusual, counterintuitive if you ask me. So let's ignore all of that and just look at y equals cot. Here it comes, that's y equals cot, it's a bit smaller. And we're going to use that under graph transformation to complete this bit of notes. So we are moving everything by pi over 4, and it's important we get the right direction. It is to the left is the translation. So it's like we're picking up the red graph, taking it 1/4 pi to the left. And from then on, it's fairly straightforward.